Hi all, welcome to part 7 of the video lecture on counters. See, in part 6 what we discussed, hope you remember, it's about the counting, right? 2-bit counting, 2-bit down counting is what we saw there. By observing the timing diagram, that frequency division and how it is doing that counting. Hope everything is clear. So please come to this video only after finishing the previous one. Okay, I am repeating it every time. Okay, yeah, that about it, and the corresponding state diagram. Then I ask you to try out with one more flip flop and also with the negative edge triggering. Okay, hope you tried it. Now it's time for me to introduce something, a small concept called transient states. Okay, so what is the problem with the this asynchronous counter? Something I told you already. So when you are connecting clock only to the first flip flop and output of which we are connecting to the second one, like that. So this is the asynchronous configuration. But the problem is here there is something called a rippling effect, right? Some delay problem will be there. So we call this asynchronous counter as ripple counter also. So this one is your asynchronous counter, right? So another name for this asynchronous counter is ripple counter. Why we are calling so? Because that rippling effect, right? Ripple counter, the delay involved. So every flip flop can work only after finishing the working of the previous one. Otherwise, if it is working immediately before that, it will go to something different, right? So that is our transient state. Okay, so if that is not the case, so in between something different can happen. So let's observe it. So far in our discussion we assume that there is no delay. All of them are working very fast and this delay is very much negligible. And suppose it is not the case, that because in reality definitely this flip flop it is made out of some cross coupled NAND or NOR, that kind of configuration, that individual gates will have some delay. Accordingly the whole flip flop will have some small delay, right? So that delay you can't ignore completely. Now if you are taking the delay also into consideration, let's see what will happen. So far here we didn't assume any delay, simply immediately during that clock edge we are executing the flip flops. Okay, now when that delay is introduced, how the timing diagram for a 2-bit counter will occur, like that is what we are going to see now. So let me take the original input to clock now. Let's take a small clock pulse like this. So to understand these things you should draw this timing diagram properly. Why I am spending this much time is I want you to understand it clearly. I don't want you to by heart anything, okay? So that it will be interesting for you. 1 second. Yes, so I just completed the diagram in between. Anyways, this is our original clock, right? We are having, and we are going to observe what is our Q0 output and what is our Q1 output, okay? And for that, let's take a different color. So what we saw so far is during rising edge of the clock, the flip flop will be triggered, right? And hope you remember what we are having is just 2 T flip flop cascaded. So this is the first one, this is the second one. And for the first one, this particular clock we are applying, and for the second one, this output Q0 is what applied as a clock, okay? And this Q0 you are taking out and you are observing what is this Q0. Similarly, this Q1 you are taking out and observing, and you saw that Q1 Q0 together is doing that counting for you, okay? So this is your flip flop 0 and this is your flip flop 1, and also that high voltage is being applied for both the flip flop, so that it is in the toggle mode. Okay, so now let's observe what happened during every rising edge of the clock, like this. So you can see that initially it is in a low voltage, right? Now as soon as the trigger clock trigger happens, the flip flop is first flip flop is supposed to toggle, but what we are discussing here is the rippling effect, okay? And is there any problem out of it? That is what we are observing in detail. So assume that the flip flops are having some considerable maybe minute value only, so very small delay involved. Okay, so there will be a small delay, so it's supposed to toggle, but this input should reflect the output, right? So the toggling will happen even though the clock triggering happen, immediately output is not going to toggle. After some small amount of time the toggling will happen. Why that small amount of time? That is a delay for processing the input to the output. You know, the flip-flop will take the toggling input as well as the clock and the present state, everything, and then only it will analyze, observe, and it will change that state, right? So that will happen some small time. So what I'm doing is, instead of immediately drawing like this, I am just moving it little bit further. Okay, so for you to understand, because the toggling happens but after some small amount of time, and now this will continue like this. Again, at this point it is supposed to toggle, but due to the delay I am extending like this. Okay, fine. Again it will continue. After that delay it will toggle. Again it will continue. So why I am crossing this boundary? This small value is my delay. Okay, hope it is very much clear now. Okay, let's continue like this. Everything is square wave only, but because of my drawing it's looking something different. Anyways, I am reminding you. Yeah, that about it. Now let's see the behavior of Q1. So what will happen with the Q1? Let me take a different color for it. Okay, fine. So this Q1 is being triggered by this. So for that, let me draw something like this, because this is the point the second flip-flop is supposed to trigger. It's now different from the original one, right? In the previous case we taken everything same line we drawn, because all are getting triggered at the same time, right? But here it is not. The triggering is happening after some time, so that is why I'm sorry, I don't have to think about this part, because this is a negative edge. Okay, so I have to worry about the positive edge only. So just observe the positive edge of the second one. Okay, this one, and then after this one only. So this is the point where it is supposed to trigger, and again here. Okay, sorry, again I drawn that negative, so it's negative edge, sorry for that. So this positive edge, and then this positive edge. Okay, so this is where we are trying to see the behavior of the output wave, Q1. And as usual, this Q1 is continuing in its low voltage, and immediately when it is getting the triggering, it is supposed to toggle, right? But again, as I said to you before, there will be a small delay. It's not going to trigger immediately. Instead, it will proceed for some time. And why this delay? Because of the delay of that particular flip-flop. So flip-flop 1 will have some delay to process the input to the output, and that is what is highlighted here. So after this much time, why this gap? So that is for that processing purpose, right? Similarly, it will continue. Again, now it is supposed to trigger, but it will extend like this. Okay, again it will toggle, it will continue, then it will toggle after that delay. Again it will continue. So this is actually your rippling effect, right? So that delay that is getting accumulated from one to another like this is what we call as a rippling effect. Okay, hope the idea is clear now. Okay, now accordingly, if you are looking at the counting sequence, there could be something interesting. So what we saw initially is both of them are giving you a state like 0 0. We started with that, right? Now this Q0 is changing to 0. From 0, Q0 is changing to 1. What about Q1? Q1 is also changing to 1. But now the interesting thing is, in between, see this small window, how can I highlight it? So everywhere I am highlighting some portion like this. This portion. You just observe this. Okay, this gap, and similarly here also this is getting changed. So at here no problem, because it's simply retaining that information, but at this point again it is changing to high, and this is changing to 0. If I am drawing like this, it will complicate things. Okay, yes, let's continue here. See, I just highlighted that small changing period, or where we are having some issue, that is by this green signal. Okay, let's see. So initially both are in 0 0 state. Okay, so both the flip flops are initially in 0 0 state. Now from 0 0 we are supposed to change it to 1 1 1. Hope you remember, because in the previous one we saw that 0 0 it is supposed to change it to 1 1. But is it changing? So that is the question. So this Q0 is changing to 1, right? But during this small duration of time, so this is very much negligible compared to the actual time period. Okay, so it's a very small time. Okay, during this small period of time, which I highlighted like this, during this small period of time, Q0 is changing to 1, where Q1 is retaining that 0. It's not updated. Okay, now after the small duration of time, Q0 will retain that 1 and Q1 will change it to 1. Fine. So if you are looking at it, actually we are expecting that 1 1 as the next state of the flip flop, but instead of that we are getting something like a 0 1, and that 0 1 is actually, it will last for a very small duration of time, that is this 0 1. So we call this one as a transient state. It's not permanent, right? So this will immediately disappear. Okay, so after that it will go nicely to that 1 1, the next state, the expected next state 1 1. Now from 1 1, where it is going 1 1, this is changing to 0 and this is changing, it is retaining that 1. So as it is retained in the previous value, here we don't have any confusion, because this previous value, if it is having a change, that change will occur little bit delayed. So that is a problem we are having. So as it is retained in the previous value, there is no issue. So after that immediately it will go to 1 0. Okay, fine. Q1 Q2. Now again we have that issue, because here this Q0 will toggle to 1, and we are expecting this to toggle to 0. Okay, but that will happen after a small duration of time, and this duration is again critical for us. And let's see what will happen. So during this duration, this is 1 and this is also 1. Okay, so it's not changing. That change is happening after some small amount of time. In between it is showing again some transient state which lasts for a very small duration of time, and that is found to be 1 1 here. It is something unexpected. We don't want it, right? So yeah, then this is retaining that 1. No, it's proceeding with that 1, and here it is toggling, and the toggling is happening after some time. So this is the next valid state we are in need of. That is our 0 1, right? Now from this 0 1, next time there is no such issue, because it is simply retaining and this is changing to 0. So it will go back, and again it will repeat this cycle. And this 0 1 and 1 1 we got in between is what we call as the transient state. So this is our transient state, because it's valid only for a small duration of time. It is not going to last for a larger amount of time, and it is something not needed for us actually. So for our actual counting sequence, we need something like 0 0 1 1 1 0 1 0 1 0 0 like that. So in between, what is this? This is something unexpected, or it's something we don't want, right? So we have to eliminate it, but there is no other way, because as it is asynchronous counter, everybody will depend on the output of the previous one. So definitely that delay will be there, or that rippling will be there, and as a result of this rippling, this transient state will come. Okay, so there is no other way to eliminate it. Otherwise you have to reduce the delay, or even I didn't explore further how this asynchronous counter itself can be made without this transient state. But anyway, I have a solution for you. It's like synchronous counter, where you can as the clock's pulses are connected to all flip-flops simultaneously, all will trigger simultaneously, and it will lead to this state change, counting everything without introducing any transient state. So asynchronous counters have this transient state problem, delay problem, rippling problem. All those things are eliminated by the synchronous counter. But it is something different. We want all the flip-flop to be work in synchronization with the clock. Okay, so that is the difficulty we are having. So same thing you can try with the 3-bit counting also. So here why I given, I thought of explaining this asynchronous counting part. Anyways, it's clear, right? So if you are looking at the state diagram, I was trying to say something different, because initially it started with the 0 without looking at timing diagram also. You can now draw this. For that, what I am doing is 0 0 this is your Q1 bit and this is your Q0 bit. At every time this Q0 will toggle. Now during this toggling, Q1 is also supposed to toggle because Q0 is changing from 0 to 1, so Q1 is supposed to change, but that change will happen after some time. Still that it will retain that 0. Okay, so after some time it will change it to 1 1. Okay, fine. Now what is the next state? Next state is this Q1 is toggling to 0, but what about your Q0? Q0, that 1, it is retaining, so there is no issue. So whenever there is toggling, that time only that delay is going to affect you. Okay, next that problem will happen because your Q0 is changing to 1, but Q1 is supposed to change it to 0 because of the 0 to 1 transition, but that will happen only after a small duration of time. Till that it will retain this 0, right? This is something we don't want. And it will retain, so it's supposed to toggle, it will retain that 1, this 1 it will retain, so that is a problem. Okay, and then it will nicely change, this will change it to 1 and this will change it to 0, and then after this, and there is no other issue. So this is what I was trying to say, and hope you get it, right? Yeah, so there are so what we got is 2 transient states you got, and sometimes in gate exam and all, this is very important. They may ask you because all the straightforward things so they may ask you how many transient states can be there in a 2-bit counter, like that. So here we observe that there are 2 transient states in modulo 4 counter. Particularly this is a down counter, and I ask you to execute all those things with negative edge triggering, and you will see how that up counting and its transient state, everything will occur. Here something for you, 3-bit counting. Let's quickly see the output. I am not going to show you the timing diagram and all. Hope you know how it is working, and I already given it as a homework also. So you can just see this bits like Q2, Q1, Q0 and the clock also, right? And you have to observe that for which sometimes they may twist the they may confuse you by giving the clock to some other flip-flop. Then you have to take care. So you should always take this which one has the least significant bit. The least significant bit should be the one where the clock is directly connected. Here the clock is directly connected to that Q0, that is why I am taking it as LSB, and the one which is far away from the clock should be treated as the most significant bit. Sometimes they may give in the reverse direction also, so that time you should know, you should do it without making any confusion. Okay, so that's why I am telling you. So accordingly you have to take. Okay, so and you know that initially you can assume as it is positive edge triggering, there is no confusion at all, it's just work like before. Negative edge triggering you can try out. Okay, so we initially assumed that everybody is in 0 0 0, so that this Q0 will always toggle. Okay, so there is no doubt on that, so like that it will toggle. Okay, so let's see how many toggling needed. This is some 4, one more time. Okay, let's see that. It will always toggle like this. Now what about this Q1? Q1 is triggered by Q0. So whenever this Q0 is having a transition from 0 to 1, 0 to 1, and that time only Q1 triggers. And then it will retain. Again during this transition from 0 to 1, it will trigger, means it will toggle. Okay. Then it will retain. Again during this transition, it will trigger, means it will toggle. Then it will retain. Again during this transition, it will trigger and it is toggle, and then it will retain. Okay, and finally what about Q2? Q2 is now depending on Q1 output, right? So it is being triggered by Q1. So whenever this Q1 is having a transition from 0 to 1, that time Q2 will be triggered, and then it will retain, because here and all there is no 0 to 1 transition. Now we have a 0 to 1 transition again at this point only, and that time it will trigger again, and then it will retain like that. Okay. And now you can see that these things are like this is your so if you are observing these numbers, this is your state diagram. If you are observing some 0 0 0, it is changing to 1 1 1, and from here it is changing to 1 1 0. So I am observing like a Q2 Q1 Q0 like that. Okay, everywhere it is Q2 Q1 Q0. Then from here it is changing to 1 0 1 like that. Okay, like that, and finally it will reach this 0 0 1 and back to this. So in between transient states will be there, because we didn't analyze that way. That you can try out, and you can see how many transient states you will get in this case. Okay, so that is because of the delay. Hope you get the idea that you can work out now. So it's a counter that is counting like 7. This is your 7 6 5 4 3 2 1 0, right? So this is a what is this? What we obtained is a 3-bit down counter, because going from 7 it is going towards 0. Down counter. How many different states it's gone through? 8 different states, right? 0 to 7. So modulo 8 down counter. So we discussed all the 3-bit counter in different variation. Again, you can think of different cases, like how many transient states here, what about a 4-bit counter, 4-bit up and down counter, like that. All variation I request all of you to work out by yourself. Okay, yeah, that about it. In the next video we may see that synchronous counting. Thank you.